Well, here's the last talk of the session. Kris will present us his work.
Okay, thank you very much. So let me also first thank the organizers for organizing this workshop and giving me the opportunity to present some of our work. So I will be talking about a numerical method. I will explain how it works to solve the Fermi polaron problem, and this to an extremely high precision. Okay, and this method will be using a diagrammatic series, and I will also explain what is the large order behavior of this diagrammatic series. So this work has been done in collaboration with Riccardo Rossi, who was a former student and who is now a postdoc in Lausanne, and Felix Werner, who is my colleague at the ENS. So I guess everybody knows what the Fermi polaron is, but let me remind you nonetheless to be on the same page. So we are talking about a mobile impurity, which is immersed in a Fermi sea. And so we have a non-interacting Fermi gas to which we add one impurity here in blue. I will refer to this impurity as spin down, and to the particles of the non-interacting sea as spin up. So then we turn on an interaction between the impurity and the particles of the sea. And this interaction is a short-range interaction. So we take the zero-range limit, it's attractive, so that we can model this interaction strength by just one parameter, which is 1 over kFa, with kf the Fermi momentum of the Fermi sea, and a the S-wave scattering length. Now what happens? You all know what happens. So because of the interaction, there will be particle hole excitations of the Fermi sea, and these particle hole excitations will dress the impurity, and hence it becomes a quasi-particle with a different effective mass and energy, etc. But what was less obvious is what happens if you increase the interaction strength. And actually, it was shown for the first time by Prokofiev and Svistov in 2008 that if you increase, you can actually have a transition to a state where this impurity will form a bound state with one particle of the Fermi sea, forming a dimer, and this dimer will again be addressed with particle hole excitations of the sea, hence forming what one could call a dimeron. And this has also been observed, this Fermi polaron, experimentally using ultra-cold atoms, for example, in the team of Martin Zwierlein. Now, so to show that this transition happens, Prokofiev and Svistov, they developed a method called diagrammatic Monte Carlo, where they evaluate a series of Feynman diagrams. And with this, they could solve the problem. And this here you see the result of such a calculation. This was done by my student a few years ago, using essentially the same method as Prokofiev and Svistov, confirming what they found earlier. So here you see the energy of the Fermi polaron. This is the energy minus the binding energy in units of the Fermi energy of the Fermi sea. And one sees that there is a transition at some critical interaction strength where indeed the molecule or this dimeron becomes the ground state. Now, using the same method, one can calculate the quasi-particle properties such as the polaron residue. And the polaron residue is nothing else than overlap of the polaron wave function or the polaron state with a non-interacting state. And here you see this is again a result of the diagrammatic Monte Carlo simulation. We see that if we increase the interaction strength between the impurity and the particles of the sea, that the Z factor drops. And moreover, if we compare with Chevy-Ansatz, which is basically the lowest order diagram, we see that this is extremely accurate everywhere. So that's really quite remarkable that even when the Z factor is very small, meaning that particle hole excitations become very important. It is still accurate, even quantitatively. It's accurate to describe just an ansatz with one particle hole excitation. So let me, before going to the methods that we use to solve this problem, let me introduce the model itself. So we will just have a Hamiltonian, which consists of three pieces. On one side, we have the first term, which is just the kinetic term of the impurity. Then we have the kinetic term for the Fermi C, and then there is a coupling between the Fermi C and the impurity. And to model this, one can do this in various ways, but the way we typically do it is to start from a lattice model, and we introduce a lattice model for avoiding ultraviolet divergences. And it's basically a Hubbard type of model where the first term is just the kinetic energy of the spin up and spin down. And then we have an on-site attractive interaction. So G0 is negative. So when the spin up and spin down are on the same side, they will attract each other with a strength G0. Now we, of course, we want to take the continuum limit. And one way to do that is to sum a particular class of diagrams known as ladder diagrams or bubble diagrams. So here you see these diagrams. So the dot here represents the on-site interaction with strength G0. And then we have in black here the spin down impurity, and in blue these arcs are the propagators of the Fermi C. And if we sum all of these ladder diagrams, then we end up with an effective two-particle propagator, which I will call gamma naught. And the nice thing is that this gamma naught is well defined in the zero range limit, meaning that we can take the lattice spacing B going to 0 and then choose G0 such that the S-wave scattering length is fixed. So we will take B going to 0, G0 will actually also go to 0 minus, and then gamma 0 depends only on the S-wave scattering length A. So we have now constructed the theory directly in the zero range limit. And to solve the full problem, we just need to construct all the diagrams, all the Feynman diagrams built from this gamma naught and the three non-interacting propagators. So for example, if we are interested in the one particle propagator, G, from which we can extract the quasi-particle properties, we just have a series of all of these diagrams built from these boxes, gamma naught and the three particle propagators. So there is one rule which we have to use, that is that we cannot include any ladders anymore. So this is because any ladders have been included in gamma naught. So if we have a ladder in a diagram, it should be excluded, otherwise we are double counting. Okay, so now I will just briefly outline the idea of diagrammatic Monte Carlo in the more conventional sense, the way it was introduced by Prokofiev and Svistanov. So the idea is that we have AN. AN is the sum of all diagrams of order n. And so to get this, we need to sum over all the topologies, tau, integrate out all the internal variables. Typically, conventional diagrammatic Monte Carlo works in momentum imaginary time representation. So these integral over the axis are just integrals over internal momenta and integration over imaginary times. So then if we, after integration, we see that we just have this integrand, which is just the product of propagators as given by the Feynman rules. Now, the way then the calculation works is that we will just do like a classical Monte Carlo, but we have to define a configuration, and a configuration will just be a particular topology and particular values of these internal variables. Okay, and then we do a random walk in this space of configurations, and these configurations are then visited with a probability which is proportional to the absolute value of D, which is just the product of the Green's functions. So I will not explain exactly how these updates are constructed, but that's the idea. So the idea is that we have Monte Carlo updates which can change the diagram order, diagram topology, and the values of these internal and external variables. And by making such a random walk and keeping a histogram, we can evaluate all these coefficients an. Then if the series is convergent, you just need to sum them, and that's it. But that's something we will discuss later. Now, there was a second approach, which was introduced more recently by Riccardo Rossi in 2017. And this technique, which we call CDET, is far superior to the conventional diagrammatic Monte Carlo. And the reason is that the configuration is defined differently. So before, the configuration included the topology, but now we will just say that the configuration is nothing else than just the values of the internal variables. And what we will do is visit now configurations with a probability which is proportional to absolute value of the sum over all topologies at a given order of these functions D, which are just the product of propagators. So now we have one axis in this intuitive picture, in this intuitive representation. We have one axis less, where we just do Monte Carlo updates, changing the order and just changing the values of these internal variables. And typically for the CDET method, we work in position and imaginary time representation. Now, what I will present is a method which is inspired by CDET, but now specific to the Polarone problem. And we refer to the method as PDET in this case. So for the Polarone, the situation is a bit simpler because we have a backbone. So this backbone represents the impurity, which is moving forward in time. And so it goes from an initial point 0 to some other space-time points and ends up at the space-time point x, but it's always moving forward. And therefore, actually, it's impossible to have disconnected diagrams because all the Feynman diagrams will be created by taking these open ends and connecting them in a particular way with a spin-up propagators. So we can see that because of this impurity which moves forward, there are no disconnected pieces which are present in the many-body case. So how would we then write down the contribution of the order n? Well, like I said, the configuration is a set of space-time points for all of these vertices. Then we have to integrate out all the internal variables to get the nth order contribution to G. And the contribution to G is nothing else than this backbone B, which is the product of G0 down, gamma 0, G0 down, gamma 0, G0 down, etc. That's what we see here. And then to have all Feynman diagrams, we have to consider all possible connections of these open ends. Now, this can be done in a single shot by just calculating one determinant. So if you do one determinant, you have all the topologies. And so it's the determinant of the matrix A, where the matrix elements are just given by the spin-up propagator. Now, in this case, we are making one error. That is that gamma 0 includes all the ladder diagrams. So I said that we should not connect, for example, this open end here with this open end there, because otherwise we have, again, a ladder. But this can be cured very easily by just setting a number of matrix elements to 0, namely if aij with I equal to j plus 1, we set it equal to 0, and then this situation can never happen. So that's a very simple trick, and that's it. So then we see that summing all the, given a set of space-time points, if we have to sum all the topologies, it's just the number of operations it costs is just of order order to the power order cubed. Okay. So that's not costly at all. Now, what if you are interested in self-energy rather than the Green's function itself? The self-energy is interesting because we can more directly get quasi-particle properties from it. And here the situation is the following, that we want to, again, have all possible connections of these open ends, but we want to avoid having reducible diagrams, okay? Meaning that the diagrams should not fall apart if we cut one of these lines. And so the situation then is that to get the order n, or all the diagrams of order n for the self-energy, we again need to integrate out the internal space-time points. Then we have a backbone, just like before. This is the product of gamma zeros and G0 downs. But then this part is different. S tilde is now are all possible connections, but in such a way that we avoid having reducible pieces. And this can be obtained very easily in a recursive way. So if we take, for example, here n, little n equal to big N, which is the order of, for example, 4 here in this example, then we see that this Sn here is just the determinant of the matrix A. So it will create all the possible connections, either reducible or irreducible. And then we just subtract all the reducible possibilities, meaning that we look at irreducible connections up to a certain vertex k, and then multiply with all possible connections, reducible and irreducible, for the remaining vertices. And if we do this in a recursive way, starting from little n, from 1 to big N, then ultimately we have S tilde big N, which is all possible, the sum of all possible irreducible connections. Now, what's the computational cost of that? That's very easy to see. We just have this recursive formula. So we have to sum little n from 1 to big N, and then we have this sum over k. One determinant costs k cubed, so in the end it's n to the power of 5. So it's a bit more costly than G itself, but still polynomial. So that's just the way how to get the sum over topologies. Then next step is to do the integration over internal variables. And the way we do that is just by Monte Carlo updates, and I will just briefly describe them. So what we do is we have this backbone, and then we have to look at all possibilities of these space-time points. So we basically have 3 updates, and that's it. So it's easy. The first update is position shift. It says that just pick one of these lines at random. For example, this one here. This has a position difference of delta R old, and then we propose a new position difference, delta R new, and this we just choose it following the short time behavior, short time and short distance behavior of G0, in case that we chose a G0 line, or gamma 0 in case we chose a gamma 0 line, with delta tau, the time difference which is given. Second update, time shift, again, choose one line at random, and then propose a new time. So given the delta tau old, we choose a new time difference for this line, again proportional to the short time and distance behavior of the propagator gamma naught or G naught. And then we have another update which says that we also have to change the order. So we just take the backbone and add 2 pieces at the end of the backbone, which is a gamma 0 line and a G0 line. And then again, to choose the position difference and the imaginary time difference of these 2 new pieces, we use the short time and distance behavior. And then we also have to, if we add the order, if we increase the order by 1, we also have to have a move, complementary move to reduce the order by 1, and that's just remove. Okay, so now I'll go to results. So this is the Green's function at unitarity. So KFA is equal to infinity. This is the nth order contribution to the Green's function for momentum 0 as a function of imaginary time for order 1, 2, 3, 4, 5. Okay. And what we saw immediately is that the contribution drops very rapidly. And we actually believed that it would be convergent, and let me go to even higher order. So since the scaling is polynomial, we don't have any problem to go to really high order. In this case, order 30. And this is Gn now integrated out over imaginary time. So it's for frequency 0 as a function of the order. And indeed, it seems to converge extremely rapidly to 0. However, if we zoom in, we see that this is actually not true. And we see that at a particular order, which is pretty high, order 15, the series becomes sign alternating and even exponentially divergent. And this was actually much to our surprise. Self-energy has a similar behavior. If you don't zoom in too well, then you think that it's nicely divergent, but in fact it's sign alternating and it's, sorry, I said that you have the impression it's convergent, but if you zoom in, you see that in fact it's sign alternating and divergent. So then, in order to understand where this divergence comes from, let's go back to the imaginary time. So again, this is Gn as a function of imaginary time for momentum equal to 0. But this time I only plot high orders, so from order 21 to order 30. And you see indeed that there is a bump here at a particular maximum at a particular time. And this function of imaginary time seems to be sign alternating and just increasing. And this is really something a priori very strange to us. So the behavior that it has at large order is actually just a function of time, which is rescaled in an exponential way. Okay. So if we plot, we take the absolute value of this Gn and multiply with r to the power n, we see that all the data nicely collapses on top of each other, which is this function f of tau. And the value of r here is indeed somewhat smaller than 1, showing that the series is divergent. So how can we explain this behavior? So let me first explain why we were thinking that this would not happen. And the reason there was an argument which was explained in this paper here. And we also thought that this argument was valid. The argument in favor of convergence goes as follows. You always have a backbone in the diagram of propagators that move forward in time. Okay. And we have to integrate out all the internal times. So if I just simply replace the propagators with 1 and I forget about momentum integration, then this simple integral over imaginary times in an ordered way will give you tau to the power 2n over 2n factorial for a single diagram. It's simple to see that because I will use a similar argument in what comes next in a slightly more complicated situation. But if we say that the order is high and these typical times are short, so the typical time of each line would be delta tau of n. I have 2n lines, so 2n times delta tau must be equal to, or of the order of tau. So therefore, if I have 2n of these lines, the contribution will just be tau over 2n to the power 2n, which is the same as this result up to an exponential. Now, how many diagrams do we have? We have n factorial diagrams. So this is the contribution of a single diagram. So if you multiply now with n factorial, then the total series of all diagrams would behave like that. So at order n, this is the sum of all diagrams would be of this order. So one would conclude that the series is absolutely convergent. But that's not what we see numerically. Okay. So we try to actually make this argument a bit more rigorous by including the integration over momenta. And what we did is take the vacuum form of gamma zero. Actually, I'll sit down. We took the vacuum expression of gamma, or gamma zero, and then also include the integration over momenta, if we work in momentum representation, with a cutoff. And then one can show that actually there is a rigorous bound that the sum of all diagrams will actually scale as 1 over square root of n factorial. But still the series would be convergent. So meaning that since we see that the series is actually divergent, can you still hear me? Okay. Since the series is actually divergent, we know that the convergence breaks down due to ultraviolet behavior. So short time, large momentum, or short time, short distance. I also have to mention that actually this does not apply to all diagrams. There are some classes of diagrams. For example, if we just close all of these guys with a simple loop, then we end up with diagrams which do scale as something that decreases if we increase n.
To be on the safe side, switch off this other microphone.
Just use this. Yeah. Okay. How do I switch it off? Okay. Yep. And I'll just this. Okay. Okay, so now we actually were wondering which diagrams could explain the behavior that we saw, that we have this exponential increase at large order. And two diagrams which were immediately our suspects are those two guys. And they are obtained by looking at so-called T3 diagrams. So these are like ladder diagrams, but for the three-body problem. So it's if you just consider 3 particles in vacuum, they all 3 move forward, and then you will end up if they interact. So if two of them interact with the third one, you will end up with diagrams of this type. Okay. And these diagrams can be closed in 2 possible ways with 2 backward propagators, either like this or if they exchange like that. And then if we just look at the contribution of these 2 diagrams, so this is Gn, again, the end order contribution of each of those 2, we see that it also exponentially increases. Moreover, it increases exponentially with the same value of R, meaning that the leading behavior of the large order set asymptotics is the same for those 2 diagrams as for all the diagrams. And again, we see the same behavior for those 2 guys. Here you see the sum of the 2 as a function of imaginary time. If we then rescale with this value of R, they collapse to each other, giving this function f of tau. But now, actually, I have to say that this function f of tau is not the same if we just take those 2 diagrams or if we take all of these diagrams. So it's not the full story yet. Then we were wondering, okay, is this true for all values of KFA? Now, if we go to the Polarone side, KFA equal to -1, and we look how the series diverges. If we take all diagrams or just those 2 diagrams, we see again that they diverge in exactly the same way with the same value of R. KFA infinity, we already saw it. KFA equal to 2, which is very close to the Polarone transition, Polarone to dimerone transition. They marginally agree, these 2 values of R, but if we go to the molecule side, then where the molecule is the ground state, then we see that the 2 diagrams which we considered and all the diagrams, they do not diverge in the same way. So the value of R is not the same. And actually, we try to figure out which classes of diagrams could be responsible for this stronger divergence, and we failed to find a simple class. So that's something we were not able to figure it out. So it's still an open question. Now, let me explain through a power counting argument why this particular type of diagram is interesting, in the sense that it can give an exponential contribution at large order. So I will use the same argument, saying that, okay, if the order is large, and I have 2n of these lines here, then the typical time of each line will be 2n times the typical time of this line must be of order tau, the total time of the diagram. So therefore, of course, as if n is large, the times will be short. So if times are short, I can use the short time and short distance behavior of the propagators, which we know analytically. So these are the two expressions here. And then I will consider a diagram of order n of this type, and a diagram of order n+1, again of this type. So the difference is that we have to add the structure which is shown here with a dashed line. So we have two extra G0s, so a G0 up and a G0 down, and one extra gamma naught, and two extra variables over which we have to integrate, space-time variables. Okay, so the ratio, like I said, the ratio of these two diagrams involves integration over two extra variables and three propagators. Now, the typical integration volume will be very small because the time difference is small. So we have to integrate over imaginary time. This will give a delta tau to the power 1. Then we also have to integrate over position. But we see from this propagator that the typical delta r, the typical position difference, will be of order square root of tau. So therefore, the integration over position will give me a factor delta tau to the power 3/2. Same for this guy here. So it's a small contribution. But on the other hand, since the time is short and the distance is short, these propagators G naught and gamma naught will also have a very large contribution, because of this behavior here. So we see that it has this has a behavior 1 over delta tau to the 3/2, 1 over delta tau to the 3/2, and gamma naught, it scales as 1 over delta tau squared. Okay. Now what we see is that the exponents just cancel out. And in the end, we get a contribution delta tau to the power 0. So this explains why at large r, at large n, at large order, we can keep on adding these pieces, and the only cost which will be there will just be an exponential. There will be an extra factor at each order. So that being said, these diagrams are not the only ones which have this property, this sort of scale invariance. There are other topologies, if we add simple pieces like that, which also will contribute to this to the same large order behavior. And we were hoping to find actually a simple class of diagrams which would allow us to explain the full behavior at large order, meaning that we would also understand where this function f of tau is coming from. But again, we failed. We tried a few options which seemed plausible, but we did not find a simple class if we consider only this class, that it would have the same large order behavior as the full series. Then finally, I will explain how then we can get the quasi-particle properties with a high precision, because the series which we have is exponentially divergent. And so formally we have this power series, for example, for the self-energy, which is at each is a sum over n, all orders, sigma n, the contribution at order n, times z to the power n. So if you want to have the physical answer, we need to evaluate this function sigma of z at z equal 1. On the other hand, we know that sigma n increases exponentially in this way, and r is smaller than 1. So therefore, the series is divergent at the physical point z equal to 1. And this can be cured by doing a conformal mapping. So what we will do is basically do a change of variable. We will map z onto a variable w of z in this way. There are this conformal mapping is not unique, but this is the mapping that we use. And what is essential is that we map actually z equal to 0. So this is the representation in the z plane. Here we have the representation in the w plane. The origin at z equals 0 is mapped onto the origin delta w equal to 0. And on the other hand, the real positive axis is mapped onto the unit segment between 0 and 1. So z equal to plus infinity is equal to z is mapped onto w equal to 1. And the point z equal to minus r, where we have a singularity, which will cause this sign alternating divergent series, this point will be mapped onto w equal to minus 1. And this choice here will fix the value of a here. Okay. Then we have another free parameter, which is this alpha. And this alpha will determine how much of the z complex z plane will be mapped into the unit disk. So for example, if we take alpha equal to 2, then we have this cut, or the red line here, which will be mapped onto the unit disk, and the whole complex plane will be mapped inside the unit disk. Okay. If we take alpha equal to 1, we shrink the region of the complex plane and the complex z plane, which is mapped inside. So in this case, only this half plane will be mapped inside. If we take alpha equal to 1/2, then only this region here, which has a shape like that, will be mapped inside the unit disk. But what is essential is that the physical point z equal 1 is always mapped onto w1, which is smaller than 1, and therefore always inside the convergence radius. So in the end, we are always mapping the series. The series in the new variable w will always be convergent. And okay, here you see the result of the Polarone energy. So this is the Polarone energy which we can extract from the self energy as a function of n. In red is what we could do before with conventional diagrammatic Monte Carlo, going up to order 12. Then without any conformal mapping, we can get the Polarone energy as a function of the order, the maximum order in the series. And we see that indeed it's sign alternating around a certain value. And then if we do the conformal mapping on top of that, this series is transformed into a convergent series, and we can get quasi-particle properties, for example, here the energy with a really very, very high accuracy. And everything is well controlled, and it agrees with experiments. So the error bar here, which we have, is basically determined by the bin size in imaginary time of the Monte Carlo histogram. So if you compare a bit with other works, this is our work, then we see that actually it agrees well with what had been done before, but this is really with a record precision. And I also want to mention that if you just do two-particle, two-hole variational ansatz, this is already also remarkably accurate if you compare with the exact numerical result. Then to finally, a few words about the efficiency and the average sign which we see in the simulation. And that's because usually when you have a sign which is alternating, so here, if we change the internal variables, then we can have a different sign. Usually, if you increase the order, this sign would go to 0. And if the sign goes to 0, then the thing that you're trying to measure will have a larger and larger variance, making it more and more difficult to do the simulation. However, what we noticed is that if we look at the average sign, so the average sign here is just defined as the value of an. So just doing the integration over internal variables of the functions d or here w. And if we now just define Zn as the same thing, but taking the absolute value of w, then we can get the average sign. And we see that in the large order limit, our average sign does not go to 0, but goes to a constant. And this is extremely good because it means that we can just keep on going to whatever order that we want, and we don't suffer from a decreasing sign, which would increase the variance if we increase the order. Now, how is that possible? That's again related to these diagrams which I discussed before, because if the order is very high, then these time differences and position differences are all very short. And then basically, everything will be determined by the short time, short distance behavior of the propagators. And this has a definite sign. It's not sign alternating at all. So meaning that whether you take an absolute value here or not, it doesn't have any influence anymore because everything is determined by the short time behavior of the propagators. And if we analyze the computational complexity that we have in the CDET algorithm, then we will see that the time required to get a particular error, epsilon, where epsilon is the sum of both the statistical error and the systematic error coming from a cutoff, it will scale as 1 over epsilon to the power nu, where nu is actually close to 3 in our case. Okay, so let me conclude here by saying that we have a numerical method for the Polarone, which is really superior to anything that we had before. So if you have any problem that you would like to solve, which involves an impurity in a fermionic environment, this is the way to go. It's much easier. It's really extremely precise, extremely accurate, and it's much easier to program than what we had before. So I showed you that we can get for the Fermi Polarone the energy with a record precision, and also that we had a particular behavior of the diagrammatic series at large order, which was something that we didn't expect, and the series is actually divergent. Maybe one side comment, that is that if we go to finite densities for the impurity, so if we really look at the many-body case, then the situation for the large order behavior is very different. So we had an earlier study together with Riccardo Rossi, Takahiro Ogoe, and Felix Werner, where we showed that the radius of convergence is always 0 actually in the many-body case in the continuum. So there we showed that the sum of all diagrams, it diverges as n factorial to the power 1 over 5. And this is actually not, the situation is just very different in the many-body case compared to the case of having just a single impurity. Now with this algorithm, you can do many different things. One can look at the mass imbalanced Polarone and hope to see the halon physics, which was discussed earlier in the talk by Boris. One can also do a few body physics for the n+1 problem, look at the Polarone at finite temperature. Then another open question, which we don't really know, is that can we actually do real-time calculations using a similar technique with determinants on the Keldysh contour? This is something that we don't know. And another open question is the full understanding of the large order behavior. Okay, thank you very much. Ah, yeah.
Yeah. Questions?
Can I ask one?
Yes.
Hi, Kris. So this kind of impressive saturation of the sign,
Yes.
is it a property of this particular problem, the property of a single impurity, or it's a kind of generic property of fermionic diagrammatics when you do determinantal, when you do essentially CDET?
That's a good question.
Would it apply actually? Can you expect this property in the finite density fermions?
No, no, for sure not.
Oh.
No.
So this is something extra. So because we know that even kind of if we do CDET after Ricardo's work, when we do CDET for essentially finite density fermions, the complexity is polynomial. However, here you are saying that there is something more to that the sign saturates.
But it's essential that you have, at least that's the way we understand it, it's essential to have the backbone. So meaning that there is something which is always moving forward in time. If you don't have that, I don't see how you can get this situation.
Okay. So it's a special feature of the diagrammatic.
Yes, it's basically because all the contribution of the diagrams is determined by short time behavior of the propagators.
Okay.
And that's because there is a time ordering.
Right. I see. Thank you.
Other questions? Okay. If no other questions,
We stop the recording, and as long as you didn't leave Karsten and Boris slides from you, I need.
We'll send immediately in PDF, correct?
Whatever. If you have movies, then
No, I
send
don't. But I do have an animation. So I do have an animation.
whatever animation. Then send it in PPT. We will just put on site.
But actually,
Whatever.
my presentation is the key point. Is it good enough or not?
I don't know. I never used it, but
Okay,
probably.
I will send both. I will send
Yes, we have unlimited links.
Right, and the PDF. Whatever works better.
Yes.
Okay, very good. Thank you.
Так, stop. I should stop recording.